so is now being recorded. So thanks for coming, everybody. This is the last EECS Tech Talk of the quarter. We'll be starting up again in the winter. Haven't thought of the theme yet. I'll be working on that, but we'll have some interesting talks. But we're lucky today to end the quarter with Sanghyun Hong. He's one of our new faculty. We were very lucky to get him from the University of Maryland. He just graduated basically, and he's working in the area of security and machine learning, which is exactly the type of person we were looking for, because we've been trying to grow our strengths in security and in machine learning for a while now, and so he's going to be a great bridge to have here. Soon before he came here, he had a little stint at Google Brain as well, so he's got some industry background, and yeah, hopefully you'll all be able to learn about what his interests are, and you can contact him if you want to learn more about it after, but he's going to give us a nice summary of his work today. So without further ado, I'll just let you take over, Sanghyun.
Thank you, Alan, for having me on this last floor, and thank you for everyone coming to my talk. I'm a new assistant professor here at Oregon State University, and my long-term research objective is to build secure and reliable deep learning systems from a system security perspective. And today, I'm very excited to share some of my work toward this goal with you all. Oops. So we observed explosive growth in deep learning. For example, in the image classification benchmark, we see deep learning has started performing better than humans since 2015, when I actually started my PhD. And the government emphasized the importance of the AI in the future. And moreover, the number of papers after that submitted in major machine learning conferences, such as NeurIPS and iClear, are increasing exponentially. And we're now facing emerging safety critical systems that include a neural network as a key component. So Tesla released the first autopilot in 2015, and people have been working on AI-assisted robotic surgery. And US airport employ AI-based surveillance systems. And recently, even the Neuralink demonstrated that their chip embedded in the monkey's brain enables the monkey to play ping pong by only using her mind. So to assure our safety, security, and privacy using those systems, the first step is to understand their worst case scenarios. And indeed, the security and the machine learning communities acknowledge this problem and studied the failure mode of deep learning systems. Their focus is to identify properties of neural networks that can lead to critical security failures. First, they studied the adversarial examples, showing that the network's predictions are sensitive to small input perturbations. And while neural networks are super accurate, counterintuitively small perturbations on their input can fool the network predictions. Here, the most famous panda in the world turned into gibbon when a hacker adds a small amount of noise in the middle. And another example is the data poisoning attacks. So unlike the conventional software that you can imagine like a Microsoft PowerPoint, network learn correct behaviors from their training data, which means that if a hacker can inject some malicious samples into the training data, they can control the behaviors of the deep learning systems. For example, an AI chatbot learned from bad tweets become a racist really quickly in 24 hours, or your self-driving car trained on malicious data can recognize stop signs as a speed limit. And it's very encouraging that the community has started caring about those problems. But let's take a moment and step back and let's look at this picture from a holistic view. So despite all this effort in prior work, most studies consider neural network as an isolated and mathematical concept, which means that it leaves out many other practical attack surfaces of deep learning systems. So here I illustrate this problem. If there is a network, prior work concerns input manipulations and expect incorrect predictions. But in reality, when we deploy neural networks in the real world systems, it requires many other components such as hardware, software, communication network, or even humans operate your deep learning systems. And each of those components is equally subject to adversarial pressures. And there could also be a vulnerable interplay between those components and the neural networks. So in the real world, we really need a system security perspective to build secure and reliable deep learning systems. So armed with this unique perspective, my research tackles two research questions. On the system side, how vulnerable are neural networks when we deploy them to systems? For example, you can imagine some practical hardware attacks or the side channel attacks. And on the machine learning side, what are the neural network properties that contribute to such vulnerability? And to answer this question, we need both systems and machine learning expertise. And I thankfully worked on system research, proposing some security mechanisms for cloud computing infrastructures, and also worked on some neural networks and the machine learning area, try to identify neural networks' internal mechanisms, and especially when the network is under adversarial pressure. And those are the basis for building defense mechanisms that later I proposed against the backdoor or poisoning attacks. And another challenge is that each community is really working well on each area, but does not know what other communities are working on. So let me elaborate a bit more what this means. So we have the desired system properties that system people always look for. For example, graceful degradations, a system should maintain the limited functionality, even when a large portion of it actually has been destroyed. And the computational efficiency, a system is desirable when it uses the computationally efficient algorithms. And privacy, a system should protect sensitive information about users. And machine learning researchers also show that the neural network have such properties. A network has millions of parameters, so some errors on them cannot cause severe damage to a system. And there are easy samples that a shallow network can predict correctly without a deep network. So prior work uses this observation for achieving some efficiency. And lastly, we know that the neural networks are vulnerable to input perturbations. So people propose to use this vulnerability as a privacy mechanism and protect the individual's sensitive information, which I'll explain later what it means. However, all my research showed that this is not the case. So I exposed the graceless degradation property, meaning that there are many parameters in neural networks that can lead to a single point of failure, and an adversary can exploit this vulnerability with practical hardware attacks. And I also showed that the input adaptive computational efficiency is just going to be a dream if the neural networks are still sensitive to the small input perturbations. And my recent work collaborated with some Google folks showed that attack as a privacy mechanism won't actually protect the privacy at all. So today, I will talk more about these three research projects. And let's start with the graceless degradation property. So in 1990, Dr. Jan LeCun, professor in New York University, which is the father of the deep learning, ACM Turing Award professor, published this seminal paper titled Optimal Brain Damage. And this was the first work that reported the graceful degradation property, showing that you can remove 60% of model parameters without any accuracy drop. So right after this, researchers came up with a bunch of techniques based on this intuition. For example, they prune the network parameters to reduce the inference cost. They do quantization to compress the network size, or they even try to add some noise to the parameters to improve the robust against the adversarial inputs. And all these techniques achieved these benefits with no accuracy drop. And the prior work in security also examined that whether it's really hard to degrade the accuracy. So they use poisoning attacks and also cause a lot of random bitwise errors through storage media where the networks are stored, or cause hardware level failures randomly. But they show that on average, it's difficult to pull the accuracy of a network down more than 10%. However, all this resilience can give you a false sense of security because they focused on the best case where you can just remove the unnecessary parameters, or the average case perturbations, not the worst case ones. So let me illustrate what it means. So here we have a standard 4-layer convolutional neural network that has 2 convolutional layers on the left and 2 fully connected layers on the right, trained on MNIST. And this network has model parameters described as blue boxes, which is optimized during training and will be used in inference to classify data correctly. So it has an accuracy of 99%. And this illustration shows the best case graceful degradation. So you can easily find the parameters that do not cause any accuracy drop when removing them. Of course, the accuracy will be intact after this perturbation. And let's also look at how prior work in security examined the resilience. And to understand, I first illustrate the neural networks in memory representation. So you can see the model parameters such as weight and biases are loaded in the memory on the below. And prior work randomly caused bitwise errors on them and measured the accuracy and average the accuracy drop. For example, they randomly flip 5 bits in the last layer and measure the average damage to a system. Of course, in this case, the average accuracy drop is pretty small, within 5%. But this was quite convincing to me at the time, because first you may ignore the large accuracy drop because you just average them out. And there are always the cases where you just flip insignificant bits. So in this example, if you flip a bit in the mantissa, the change in the parameter value numerically in a system is very small, from 0.4 to 0.5, which will lead to a negligible impact on the model's accuracy. However, for the same parameter, if you flip the most significant bit in the exponents from 0 to 1, you can change the parameter value exponentially, and showing the definition of the small perturbation in a system's perspectives can be different from a numerical standpoint. And the bit flip inflict the accuracy of a drop of 41%, which is the graceless degradation. So now we know that there a bit exists that can lead to a significant accuracy drop. And the challenge is that how you evaluate the vulnerability, right? So here I use this method. I take a model and flip each bit in all parameters of the model from 0 to 1 and 1 to 0, and measure the accuracy over the test set for each bit flip, and mark Achilles bits. And Achilles bit is that once we flip this bit, it can lead to the accuracy drop over 10%. 10% was the challenge claimed by the prior work. Then I quantify the vulnerability. First, I look at how much damage a single bit flip can inflict, which is the maximum accuracy drop. And the second dimension is that I look at how many parameters contain at least one Achilles bit, which means how many single point of failures a neural network has. So in the MNIST model with different architectures and training configurations, I found that in all 8 models, there is at least one bit that causes the accuracy drop more than 98% once the bit is flipped. And I also check how many parameters contain at least one Achilles bit. And approximately half of the parameters contain at least just one bit that can push the accuracy drop below the prior work's empirical observation, 10%. And I scaled up the experiment by examining larger models, and I had the same result, flipping one bit, make the model worse than random, and half of the model parameters contain Achilles bits, which means the vulnerability of the neural network to this bit flip is prevalent. Oops. So now my research question becomes, how can an adversary exploit this prevalent vulnerability? So to answer this question, I start thinking about the threat model of the bit flip attacker. If the attacker can control the bit flip locations, the attacker is strong. But if the attacker is not, it is the inaccurate attacker. And in terms of the knowledge, the white box attacker has the full visibility of the model's internals. They know which parameters are vulnerable in advance, whereas the black box attacker does not. So here I illustrate this space of a single bit adversary, and the vertical axis indicate the capability of the attacker, and the horizontal axis means the attacker's knowledge. And the strongest attacker is upper right quadrant, who knows which bit to flip and can flip only that bit. And this attacker can control the accuracy drop with a bit flip from 0 to 100. And on the opposite side, there is the weakest attacker, who doesn't know which bit to flip and cannot control the bit flip location. So the probability of causing a significant accuracy drop is going to be really, really small. However, suppose that the weakest attacker randomly flips multiple bits in the model, And the probability of hitting an Achilles bit increases because half of the model parameters contains at least one Achilles bit, and there are multiple parameters exist in the model that lead to this vulnerability. Therefore, this weakest attacker can become a stronger attacker. So to evaluate, I provide a practical weapon to this weakest attacker rule hammer, which can flip bits in the memory at the software level. So at the software level is really important. I'm not using any hardware mechanisms to flip the bits in the DRAM. So illustrate how row hammer works. I have DRAMs on the below side, and the DRAMs are composed of the multiple DRAM banks. So the rows in DRAM banks store the data. And when the victim actually accesses, the row is activated, the data will be sent to the CPU. And the attacker, to compromise the victim's data, he accesses the data in the nearby rows multiple times. And performing this leaks the capacitor charges in the mid-below and cause the bit flip in the victim's data. So I evaluate this attack in a practical deployment scenario where one, a victim runs an off-the-shelf ImageNet model in a VM, and second, the attacker runs another VM and randomly tries to flip it in the victim's memory. I run this attack multiple times on different DRAM chips and estimated the exploitability in the world. But I'm skipping here the experimental details, probably due to the lack of time. So we found that the weakest row hammer attacker can inflict the severe damage. On average, 62% of the attacks cause 62% of the bit flip causes the accuracy drop over 10%. And the time it takes to cause this accuracy drop is less than a few minutes. And also our attack is difficult to detect, which is also important. In only 0.08% of cases, the attacker caused the program crashes. In most cases, the victim will not know whether they're under attack or not. So which means that the attacker can just launch this random row hammer attack that randomly flips the bits in the memory. And once they come back, while running some attacks more than the minutes or the few hours, then the program will not crash, but the neural network accuracy will be really, really low. So here are the bottom lines of my first work. So first, I show that the neural networks are not resilient to worst case parameter perturbations. So all networks have a bit whose flip causes the accuracy drop more than up to 100%. And 40 to 50% of the parameters in the models are vulnerable. And we also show that this vulnerability to fault attack is understudied. So one can inflict the vulnerability with the weakest attacks, such as a blind row hammer attacker. And this attacker can exploit this vulnerability in a practical setting. And which means that in a broader sense, we need the solutions from both systems and the machine learning side. From the system side, defenses that prevent flipping a bit flip are not sufficient. So we need to think about the broader defense mechanisms. And in the machine learning side, future work is required to build a robust against this new hardware attacks. So before I'm going to talk about the second work, if there is any questions, I'm happy to answer it.
I have a question. This is Bashir.
Sure.
Interesting. So I'm just curious. Again, it's not really my area, but especially the software side of the thing. So I understand the attack here. I'm just curious if you could comment on, I assume there might be security countermeasures on the software level. So I think what you're talking about is what if somebody goes and changes some bits in the memory right? And I assume this could fall into securing anything with respect to software, it changes or code, or it could change any codes within the system. So are there any works who try to address the security of the software in general, and if there are, how applicable those are to defend against these attacks?
Oh, that's a great question. So first of all, I actually explored several defense mechanisms, but since there is a lack of time, I explained it here. But one thing I used on the neural network, if I consider neural network as a software as well, so is even if bit flip can actually changes the parameter value exponentially, I kept the parameter, the value within a certain range. So which means that it doesn't, increase exponentially. So I implement it by using some ReLU6 like activations. So it's actually kept how neural network, how the activations of the neural network can increase. But like we also figured out that, okay, this can be a mitigation. But if the attacker can actually flip bits in the ReLU6 at the location in the memory where the ReLU6 function is, then they can change this ReLU6 function to the other pointer, such as the other activation, which is not kept. So that's the one thing. And we now believe that like software level mechanisms exist against bit flip attacks will not be sufficient enough to defeat this vulnerability, because if you imagine like bit flip can attack like any part of the neural networks or any part of the deep learning frameworks, then you can actually make anything happen. So we're looking for some hardware mechanisms at this point. So yeah, so I think that, yeah, that's the conclusion we had. So software level mechanisms, there exist in the systems research, but we don't think like that could actually defeat this vulnerability.
If a mechanism could protect against changing anything in the memory, right? Would that address would that mitigate the attacks that you're talking about here? Why wouldn't it be specific to a deep neural network? If I protect against changing any code within the memory, that should do for anything else, right?
Yeah, I really hope that there could be such mechanisms. So far, what I've seen is like error correcting code that cryptographically like examines the integrity of the data in the memory. But I guess like if you can flip multiple bits in the same row, like this parity check kind of mechanisms will fail too. So I really envision like there could be hardware level mechanisms that use advanced some schemes to protect this threat. Yeah, but that's a really good question. Yes.
Thank you. Thank you.
Thank you.
Quentin, you have your hand raised. You want to ask a question?
Yeah, so I was wondering if you could provide any sorts of explanations for why flipping single bits in some models is able to reduce the accuracy that much. So for example, if I were trying to sabotage the accuracy of a model and I could only flip a bit, what I'd aim to do would probably be like increasing the bias for a particular class as much as I could. And well, that would cause a lot of issues for like an ImageNet classifier.
True.
So did you see any patterns that you could put a label to in the sorts of bit flips you saw?
Yep. I really like the question. Oh, sorry for cutting. Do you have another question?
Oh, just saying thank you.
Oh, yeah. Thank you for asking this question. There are lots of follow-up works, like whether we can use specific bit flip to actually cause the bias. Bias means like biased classification. Sometimes it could lead some backdoor attacks if you have a certain, the input, and then you can actually make those inputs always classified into the one classes. And we actually examined all these cases, but we wouldn't think that that's too much interesting in the security perspective. I mean, I don't, judge those works, but like those works usually requires 100 bit flips in a model. Then if you can flip 100 bits in a system, that means your system is very vulnerable. No one's gonna use those systems for doing any security kind of things. So that's why we more focused on the single bit flip, but I think that there are lots of follow-ups about how we can make a biased classification. You can search on the internet. Yeah. All right. So thanks for asking many good questions, but like since we are a little bit running out of time, so I'll just explain my second work. We can always come back here like later on. So in the second work, I'll show that the misclassification is not the only attack objective. So the attacker can jeopardize the computational efficiency by exploiting known properties of neural networks. So the computation efficiency is a growing concern in deep learning. So as we can see in this left figure, the error rate on the popular image classification benchmark ImageNet has been decreasing. But behind this advancement, we have neural networks with more layers. And the recent article from Harvard warned that training a network can emit as much as carbon 5 cars in their lifetimes. So me and my colleagues studied why deep neural networks are computationally expensive, and found the overthinking problem. A network uses the same computations for every single input that is unnecessary for the simple inputs. So for this simple lemon on the left side, a shallow network with just 2 layers or 1 layer is enough to make a correct classification. And to address this problem, we proposed the multi-exit architectures. So those architectures have a multiple side branches, which is called the early exits, and where we can preemptively stop forward propagations and make a classification. And the key idea behind this is the input adaptive difference. So simple inputs consisting of majority of the CFART images can be correctly classified at the early axis. They don't need the deeper layer processing. But the complex inputs will be processed by the deeper layers, and networks make correct classifications on them. So harnessing this input adaptive mechanism, multi-exit networks claim that they can save the computations up to 50% while preserving their accuracy. And because of such benefits, these architectures receive attention from the community. So in natural language processing domains, complex and large BERT models uses multi-axis to enable faster and efficient inference. And besides, the prior work also partitioned multi-axis networks to bring the deeper and complex networks to IoT devices. So previously, IoT devices need to send all the inputs to the cloud for getting the classification result, which introduces the network latency. But if we partition multi-axis networks, deploy the shallow version to IoT devices, and the rest and deeper version to the cloud, they have the latency benefit as complex inputs will only be sent to the cloud. However, no one looked at such benefits of multi-axis model from a security perspective. And my intuition was that the benefit rely on inputs, and we knew that neural networks are sensitive to small input perturbations. So my research question becomes, are the computational savings provided by this input adaptive multi-axis network robust against the adversarial input perturbations? If an attacker can craft adversarial examples that bypass early access, the computational efficiency from this emerging architecture will be dev/none. So in this work, I propose a new threat model, slowdown attacks, that an adversary wants to offset the computational efficiency of multi-axis neural networks. And since it's the first work on proposing this threat model, I provide the tools to study this vulnerability systematically for other research. And the reason is that I want to provide the tools for system researchers who use multi-axis models for their systems in the real world and use my framework to examine the vulnerability easily. First, I presented a deep sloth, a novel attack that crafted adversarial examples that can bypass early exits. And I also proposed the efficacy metric, a standardized one to compare the impact of our attack across the different data set, different architecture, or different mechanisms. So to design the deep sloth attack, I first look at how multi-axis models make classification on early exits. And those models use a pre-trained threshold T, which is the confidence base to solve forward propagations. For example, at one of the early exits, if the prediction confidence of this panda image is higher than the threshold T, the network stops computations and returns the prediction. Here's your panda. And I examined what if we just use existing adversary examples. So here I'm skipping the details of PGD attack for the lack of time, but I provided a visual explanation of how it works. The attack has the objective of crafting the perturbation for misclassifications, meaning the resulting perturbation increases the prediction confidence on any other classes than a panda, and making the multi-axis models classify them incorrectly at earlier exit points. And however, this doesn't increase the computations. They need to bypass the exit in our scenario. So I made a crafting objective, push the adversary examples toward the uniform distribution over the classes. Then the classification confidence of our deep sloth example becomes lower than the threshold T at an exit point, which will make the panda bypass this exit point. But the previous modification concerns only one exit. Therefore, I updated objective to consider all the exit points together. Then the perturbation to this panda will make the confidence in all exits below the threshold T. And in the end, the adversary example is no longer a panda. It became the sloth that causes a slowdown on multi-exit models. And I also designed the efficacy metric to measure the impact of our work. And the metric is defined as the area under the early exit capacity curve that we designed also. But I'm skipping the details of how this metric captures the multi-exit network's efficiency in detail. And I intuitively provide what it means. So the important thing is that this area under this plot can become a standardized metric. The efficacy will be 1 if the model is extremely efficient, and the metric will be 0 if the network uses a full computation for all inputs. Therefore, if we use this standardized metric, we can make the efficacy of different multi-exit mechanisms compatible. So in evaluation, I used 2 popular image classification benchmark and 2 different multi-exit mechanisms. And I first examined the scenario where an attacker crafted each samples individually to cause the slowdown. So in this case, our research shows that the attacker can completely offset the computational savings by making the efficacy of multi-exit models to 0. In addition to that, the attacker can cause the accuracy drop from 4 to 99%, which means sometimes the victim uses the full computations and finally gets the bad result, which is more bad. So I also examined an interesting scenario where an adversary crafts a single perturbation and use them to cause indefinite slowdowns for multiple samples. So you can imagine the scenario like, okay, I can make a transparent film with the really small perturbation on it. And once I attach it to any camera that uses the downstream deep learning tasks, and then I can cause the slowdown effect indefinitely while this camera is being used. So I examined the scenario. They can also reduce the efficacy of the victim model by half and most. And moreover, we found that deep sloth attack is transportable, meaning security by off security wouldn't work. An adversary who does not know the victim's architecture, the victim's training data, or the input adaptive mechanism that the victim uses can still use other models to craft this attack adversary examples and try to perform slowdown attack on the victim's model. So here I also examined the impact of the deep sloth on real-world systems. I conducted a case study, an IoT deployment scenario, and I showed that the deep sloth can increase the latency expectation of an IoT network. So first I partitioned the MSDnet, one of the multi-exit architecture, and deployed the first early exit to an edge device and the rest to the AWS cloud. And this partitioning reduces the network latency. So without partitioning, a device will send every single input to the cloud, which takes 11 milliseconds on average until the edge receives the prediction from the cloud. But we deploy the first partition to the edge. This can process the simple inputs and the latency becomes 0.5 millisecond on average, which is 20 times less while preserving the accuracy. However, if you conduct a deep sloth attack, deep sloth can convert the simple inputs to the worst case inputs. And the edge device will send all the inputs to the cloud. Then the latency benefit will be 0, and the attacker can push the victim outside the system's latency expectations. And if this mechanism is currently used in IoT deployment scenario, one can cause denial of service-like attack. So the bottom line of my second work is, I show that the input adaptive neural networks are not robust against the adversarial slowdown. First, we show that our attack can completely offset the computational savings provided by the multi-exit neural networks. And this attack can be used to increase the latency in an IoT deployment scenario. And we also provided tools to study the vulnerability systematically. So I designed the deep sloth attack, a PGD-like attack that cracked the adversary examples causing slowdown. And we provide an efficacy metric, a standardized one, to compare the slowdown impact across the different mechanisms. And finally, this work implies that we need the solutions from both systems and machine learning side. And we examined, but didn't include in this slide, but we examined adversarial training is not a countermeasure. So if you use adversarial training, that the classification becomes robust, but it increases decreases the efficacy. So there is actually the trade-off. And in order to solve this trade-off, we may need out-of-box defenses to mitigate this threat, such as detecting the adversary examples for slowdown systematically in a network level. So these are the bottom lines for my second work, and I'm gonna pause it here and have some more questions about my first work or the second work so far.
I have a question.
Sure.
So you mentioned the IoT deployment scenario. Can you elaborate a little bit more on that? So what are you exactly, what an IoT device sending something to the cloud, what are you sending and what is the DNN doing here? What are you classifying?
So we examined the image classification. So we use the tiny ImageNet data set. This is just the image recognition task. And
what does the IoT device doing there to the cloud? What are you?
Yep. So that's a good question too. So I will try to refer this slide. So in the IoT scenario, so in the previous slide, it's so in an IoT scenario, if you only deploy the deep neural networks in the cloud, so every time the device need to send the inputs to the cloud. But if you try to use the multi-axis network, and one benefit is that you can split the multi-axis network in two parts. So we actually try to deploy these first components to the IoT devices. And then if the sample is simple, then we use these simple shallow networks to make a correct classification without actually sending the sample to the cloud. But if the sample is complex, then IoT devices decided to send this, the inputs to the cloud, and cloud will make a forward propagation there and returns the prediction. So that's the scenario that we concerned.
I see. Okay, I get it now. Okay, so just the computation sometimes takes place at the edge, sometimes at the cloud, depending on the resources. Okay, makes sense.
Yep. Thanks for asking clarification questions. All right. So then I'm gonna go to the
one more question. If there's no questions,
oh,
again,
sure.
just a clarification. I think it's good to have some interaction here. So these computational attacks, I'm just, again, this is more for clarification, right? So are these taking place on the training? So I assume these attacks will try to impact the training phase of these neural network models. Am I correct?
No, like this attack works at inference time, so test time. Yeah.
So the test time, so you could still, I think you talked about the threshold. My understanding is the attack essentially it will kind of, let's say, move the thresholds a little bit, and that will lead to higher computation. But those could be, if there is no attack on the training, so those will be fixed on the training time, right? And then the inference time, you're saying the attack will be on the inference time.
So that's actually a good question. So one thing I didn't actually go deeper in this slide was that, okay, can we fix this slowdown problem during training time as you actually give an input? And our observation is that the standard mechanism to do that, adversarial training, so we try to use this mechanism and adapt it for our multi-axis scenarios, but we found that this is not effective. So there are the trade-off between the efficacy and being robust. So if you try to make our network robust against this slowdown attacks, but you need to sacrifice some efficacy. So input anyway need to be processed a little bit more to get robust predictions. But if you want to achieve more efficacy at the test time, then you may lose some benefits coming from the robustness. The prediction becomes, little bit inaccurate. Yeah, if adversary tries to attack. Yes.
Okay. All right. Thanks. Yeah.
Thank you. Yes.
Quentin, you have your hand raised.
Oh, yeah.
Yeah, so just to clarify what's going on here, you're attacking the model in the input space. So you're
Mhm.
perturbing an input to achieve your desired behavior. You're not
Right.
messing at all with the parameters of the model itself.
No.
Okay. Yeah, I think that's what the previous question was about.
Mm.
I also have another question. Have you at all looked at similar sorts of efficiency degrading attacks for like mixture of experts models, which are the other way of handling like the overthinking problem?
No, I actually haven't actually looked at the other mechanisms that handles the overthinking problem. But that's a really good question because I talked to some of the people in the industry, or like Google, for example, or like other people in academia. They also curious about like, oh, here are other efficient machine learning mechanisms, and what if we apply this attack to the other mechanisms? That haven't answered because this work is published in this year. So I guess like this is interesting and a promising direction what you suggested. Okay, so I will move on and let's come back if we have more questions. So in my last work, I will show how a defense privacy protection mechanism designed without a system security perspective can put many users' privacy at risk. So this work actually jointly done with Google folks and is currently under submission. So your faces on the internet are free resources. I'm sorry, but I have to say that it's free. For example, my faces are on my website, my Facebook page, or my Instagram, and so on. So based on this, a lot of abundant resources. For example, a company could come up with this crazy idea, let's collect them and use these faces for social benefits. So they collect them and use some cutting edge technology for law enforcement. So if someone downloads the applications created by this Clearview.ai, and then they use those applications to take a picture of the certain person, and then you can identify some characteristics of individuals based on this thing. And that is collaborating with many law enforcement agencies too. And you may be surprised how many face images are actually collected by this company compared to 411 million with the FBI. This platform has 3 billion faces. So to protect the individual faces from this privacy threat, researchers came up with the protection mechanisms, data poisoning for privacy. So let me explain how it works. So the key idea is very simple. They first add the perturbation. You can look at the left side on your face images before uploading. And in the second phase, face recognition models will be trained on those poisoned data, which is the perturbed images. And the third part, and once trained, they can classify your perturbed images or non-perturbed images correctly. So on the rightmost side, you can see it has 75-ish protection rate. So this idea received a lot of attention from the community and media, and they also released the tools for public. So for example, you can see the images in the side. On the left side, the authors of the fakes paper released this fakes application, and it has currently over 500,000 downloads, more than that. And on the right side, Loki, which is developed by a team at the University of Maryland, and they also released this website. You can upload your face images and download the perturbed versions on it. So, okay, so let's assume that you use those tools and upload your pictures on the internet after the perturbation. And now the question is, do you think we are better protected now? So my answer would be no, because the problem is that these tools foster a false sense of privacy. So we know that the threat model does not admit an arms race here. So once you upload the perturbed images on the internet, and you're just done. And from that point on, model trainers such as Clearview.ai has a complete control over the images. It doesn't actually loop back to the victim. So we show in this case, the protection mechanism becomes def null empirically. So we first examine an oblivious scenario, which is very dumb, where the model trainer just wait until a better model comes. So for example, an adversary can wait 1 year and train a new model on these perturbed images collected a year ago. And surprisingly, if adversary does this, the protection rate drops from 75% to below 20%. And we also examine an impatient model trainer who wants to use some defense mechanisms existing in the community, for example, adversarial training and to defeat these perturbations. So in this case, the protection rate drops more than 10%, more below 10%. So we evaluate these kind of defense scenarios. We use face crop data sets and consider two state-of-the-art protection mechanisms, fakes and rookie, and 7 facial recognition models fine-tuned on the perturbed images crafted by those 2 defense mechanisms. So here's the result from the oblivious scenario. We show that the attacker with a recent clip model can invalidate the protections. So in the upper figure, we examine the protection provided by fakes, and the lower one is the low-key. And we listed the models chronologically on the x-axis. So in the upper figure, you can see the protection rate gradually decreases as you use the recent model. And there is a glitch you might figure it out. In the CELEB1M cases, the fakes actually provide 100% protection. And this is not the actual protection because fakes uses this CELEB 1 million model on crafting those perturbed images. So it's gonna be this cherry pick case. But other than that, like the protection rate gradually decreases. And on the below, if you look at the low key, which is the very recent mechanisms and more robust than the fakes, then you can see the protection rate is really higher up to the mag face model. But you can see when we use actually recently released the clean model that the protection rate is below 20% in this case. And we also examine in adaptive defenses, we consider 2 mechanisms in a broader sense. So one is the robust training. The attacker uses those public tools. This is also available by the attacker, and to perturb their own training data and train a new model and use this model to classify your face images. And second one is the detection approach. They use the robust model in parallel with the non-robust model and compare the predictions on the same samples. And if the predictions are different, then you can flag them as perturbed and then try to correct the predictions. And in both cases, the protection rate becomes below 7%. And you can see in this plot, like when we use the web-based models, the protection rate of the rookie is 77%, but like it becomes like 7% in the end when the attacker deploy those mechanisms. So we show various showcases like how the adversary can actually jeopardize all these privacy protection mechanisms. And here are the, since we are lack of time, here are the conclusions from my last work. So the first one is that data poisoning won't protect you from facial recognition. So I show that the oblivious attacker can just wait until a better model comes. And the second one is the adaptive defender can defeat the state-of-the-art protection mechanisms. And if you're trying to protect the privacy by using this attack, a holistic view is needed to designing good threat models. So we first show that the no silver bullet exists. One cannot defeat all the future models with a single defense released in any time. And we also show that the prior works threat model does not admit an arms race. Once we release the perturbed images, then you're done. So for these kind of problems, we envision that we need to find the solutions outside of machine learning. For example, first of all, like make sure do not post your pictures online, but some of them is already there, so we cannot resist against model trainer. And in order to solve this problem, we may think like restriction is required via legislation and the policy instead of just incorporating the technology on this. So these are the conclusions from my last work, and I shortly talk about the broader impacts that I created in the community with those research. So those research make an impact in both industry and academia. First, I was invited as a speaker at Usenis Enigma last year, a TED Talk for security, and talked about the practical hardware attacks on deep learning. And secondly, we are releasing our attacks in GitHub, and we are also working on building a framework where people can actually examine the vulnerability of their models trained on their side to the threats that we identified here. And our new attacks presented in my papers are incorporated into many machine learning security classes offered in various universities, such as University of Toronto or the National University of Singapore. And I'm also thinking about incorporating in my classes as well. So that's it. And thanks for listening. And I'm also want to say like happy Thanksgiving for everyone. And from now on, I'll be happy to answer any remaining questions from the audience. Thank you.
Yeah, thanks a lot, Sanghyun. That was very interesting. Yeah, all of our faces are on the internet, unfortunately, but yeah.
Yes.
So yeah, does anybody have questions? We have a few minutes left. If there are any questions out there. Yeah, I mean,
If no question, I could, Alan, just a clarification. I think that's interesting work. I mean, definitely. The last part, and I think the time is racing you, right? So you have to rush things a little bit, and I understood. The last part, I'm trying to, again, capture the concept here. So you're saying is, if I try to inject some noise on these images and train the model based on these noisy or the perturbated images, in doing so, an attacker later, when I have an image, I run it through the model, that the model will not classify it. Is that, I'm still a little bit confused of what are we trying to, kind of the model that, I guess the power that the attacker would have, right? So what does the attacker have access to in this case?
Oh, so yes, that's a good question. Sorry for not clarifying the threat model. And the threat model that we are considering here, the attacker is the model trainer. They scrape the perturbed images on the internet. And then once I mistakenly release my clean images without the perturbation, that clean image will be misclassified. A model is trained on the perturbed images. That's the protection mechanism proposed by the prior work.
Okay, I see. Okay, now it's clear. Okay, now I see what you're doing. Okay, thanks. Yeah.
Yeah, thank you for asking.
Yeah, I was curious. So, one thing that seems to be interesting from the security and machine learning point of view is that in machine learning, in some sense, I don't know if you would agree with this, but if you want to pay for security, you can put more resources into your system and build a big ensemble, for example, make it really over parameterized, very redundant, and hence make it maybe more robust. Do you think if you look at the end game of these types of attacks, that will always be sort of a viable option, and that the attacks will only be relevant for sort of resource constrained situations? What's your thoughts on that?
That's a great question. So it's the question probably about my vision and philosophy. And I think that just the putting more resources would not solve this problem. For example, you can really make the model robust against the input noise if you over parameterize the model with millions of parameters, like people see that, and this provides some robustness. But if you're doing that, otherwise, like model remembers too much about the sensitive information on the inputs, then it can actually lead to some privacy threat. So what I'm saying here is that there could be some, the trade-off between the threat that we exposed in the community. Then my 1 point lesson would be like, my research can be used as a vehicle, actually expose those trade-offs. And there we should start thinking about how we can block them by using all those, the 50 years or 100 years of, the computer science researchers in the systems area or the theory or cryptography, the other areas. So that's the the end goal, and I'm thinking that just the making model accurate and robust may not end this game. Yes.
Thanks.
Thanks for asking.
Oh, I see a hand raised. Feel free to just unmute and ask your question. Unless it was an accidental hand raise.
Oops, I can hear you. Oh, okay, yeah, now.
Yep, go ahead.
I guess if the person with their hand up isn't going to ask the question, then I'll ask another question. So that very interesting work in the privacy domain. So it seems to be focused on achieving like individual protection for the person who implements the noising of their images. Is there work in this sort of domain of more group-based protection where a large fraction of the people whose images are being scraped might apply some adversarial noise that's aimed at sabotaging the training of the image classifier itself, like poisoning their data in order to minimize the attacker's face classification accuracy across the entire data set?
So that's actually a great question. I think that I actually run this experiment, but didn't include in the paper. But we can actually provide the if a group of people wants to be protected against this threat, then we can actually protect them. But like protecting like all the people, like I haven't actually seen like how much this portion should be like compared to the entire training data set. So that things I cannot answer. But I don't see any systematically evaluation yet in the community about this problem. So it would be interesting, like if you work on it a little bit and then see in what scenarios this, the group protection makes sense, and like how you can actually provide protection mechanisms more than what we currently have, or like or reveal the problems if you provide a protection of the groups. Like that's more, I think, that promising based on what we have. But yeah, that's generally very interesting question. Yes.
All right.
Do you still have time?
So I'll just say I have to leave and go to the next meeting. But I guess as long as Sanghyun is willing to stay, anybody can stay and chat. So
Sure.
bye everybody. We'll see you next quarter. But feel free to stay and chat.
Thank you, Alan.
Thanks a lot.
Sanghyun, are you there?
Yes.
Yeah, so it's interesting. So I wanted to elaborate a little bit more. So we do have a project actually in collaboration with Wan Keen, and I think few students are here as well. We're addressing a very similar kind of issue. Not so much of the security, but I think we are kind of trying to address that as well. Except the application domain is not computer vision, it's not images. So we're looking at signals like device signals and how to classify signals, how to protect signals, how to authenticate devices based on their transmitted signals and things like that using deep learning. And what we found, for me at least, I mean, I'm trying to kind of learn a little bit on the fly on these things, but one of the things is a little bit very, very, I guess, not clear in the literature. People talk a lot about these data poisoning attacks, the adversary attacks, and a lot of those different attacks. But for me, I found it difficult to kind of digest those attacks unless they are put within a context. So the application context is often missing. And I think this applies to both the computer vision and any other domain, right? So unless you put within the application perspective, I think some of these attacks will not even make any sense, in my opinion, right? Because you have to, you could come up with design, what if this, what if this, what if this, but unless you put in the context and you think those attacks are feasible and practiced, then for me, it's irrelevant to try to address them if they're not a threat in the first place. The long story short, those threats are meaningful in my opinion only when you put them within an application context, right?
Yep.
And I think this is what kind of is puzzling me. I think I'd like to see it from an application. Again, I think in our case, we're looking at how to classify devices. And I think I will probably connect with you. I think we should probably connect, and maybe offline, I guess. I wouldn't take a long time here. We could talk about this, but
yeah,
interesting. Yeah.
Yeah, I totally agree, and I think we should the chat sometime. And then I agree. Like once they see these properties, like a lot of machine learning research is going there to understand like where it comes. Like you look at the neural networks and use these attacks as a vehicle to understand the internal mechanisms or what kind of the things going wrong. But I think that I also agree. Like the attack should be more practical. So that's where I'm actually trying to pursue. For example, this row hammer attack is practical. Like people shows that, but not right now recent for closing some of the gaps, closing the attack surfaces, but it's practical. And like there are also lots of researches, not just showing that, okay, you use this perturbation to fool the image classification model, but here are the domains maybe adversary examples can be used. And another work in data poisoning separately, like I think that very practical, showing that is from Nicholas Kalini from Google. Like I think in the Unix security, they shows that, okay, people use a lot of unlabeled data set, and you can change some of the inputs in the unlabeled data set to actually poison, the behavior of the downstream classifier. Or like in the privacy domains that people shows that, okay, you're going to use these good GPT models in the world that used for downstream tasks, for example, writing some code, then people shows that, okay, you can extract some information sensitive, which is social security number from this model because they are trained on a lot of text corpus in the wild. So like, I guess I am more, at the security side, so I like those work. But I do agree with you, like right now, probably it's a time to consider like what's going to be the practical threat if we all know this, the vulnerable properties exist, right? So yeah, so that's a great input. Yeah.
Sure. Yeah, thank you again. So yeah, that's good. Yeah.
Thank you. So yes, so I guess yes, please go ahead. Like I seen hand raised.
Can you hear me?
Yes.
Can you hear me? Okay. Thank you so much for talking. That was very interesting. Your first problem when you were talking about how some people might try to change the parameters, right? The weights. Yeah. So I was thinking about the federated learning, like where we try to train the network in the edges and then send the weights through the wireless medium to the centralized node, right? So that's kind of like the wireless channel by its nature has like some noise and interference. So when we send our weights in the wireless channel, there should be some like attenuation in the weight itself, right? So it's kind of that's an attack. It's the same attack, but by nature, but not by human. So can we apply the same defenses mechanism here, kind of to make sure that the weights that we send through the wireless medium haven't been changed through the transmission?
Oh, yes, I think that's a very good question. If I would, that's a great question. We definitely worth investigating this problem. And if I understand this problem correctly, I would first try to think about like what kind of noises that you want. So prior work shows that if you apply just random noise, which is the byte Gaussian noise to the parameter space, then it wouldn't actually reduce the accuracy too much. So then my guess is that if you apply some specific kind of signals that perturbs the model parameters in a way that your server-side model can be, behave maliciously, then if the mechanism would be practical, then I think that is a great exploitation example we should show in the community. But I guess like that's all my the guess. But I think the question itself is very interesting, and I think it may be possible if you come up with some specific perturbation or manipulations of the signals that will be introduced between the communication. Yeah.
Thank you so much for the answer. Another question is that, as Professor Bashir said, like one of the problems that we are working in is kind of our fingerprinting or device fingerprinting, where we believe that there's a fingerprint within the RF signal, and we try to kind of extract that one, use and classify devices based on that on that fingerprint. The issue is that the signal is going through the wireless channel, and then so like there's going to be always a small perturbation in the signal. So it's kind of the same as data poisoning, but it's the poisoning happened from the channel, not by another attack, right? So do you have any kind of any guess about how we can handle that one? Because this is kind of it's always going to be there. The perturbation, kind of the poisoning, is going to be always there because the wireless channel. So how we can make sure that we kind of get the fingerprint and not just like be spoofed by the channel noise?
Yeah, so that's a very interesting question. I have not clear directions if you want to pursue toward fingerprinting devices, but if you're thinking in a broader sense, like that could be used as privacy protection mechanisms. So for example, like there are the signals coming from nature, which is Gaussian noises. And if it can be applied to like distributed learning scenario or like distributed, some computing scenarios where deep neural networks on the edge devices are used, then I can use this property for protecting my sensitive information on the edge side. So it's not necessarily like the fingerprinting, but like it becomes like natural like privacy protection mechanisms. But I'm not sure like if that's the the direction that you're trying to go, but like that's one way I can think of. But other than that, like on the other side, I have no input. So yeah.
That was interesting. Thank you so much. Appreciate it.
Yep. Yes.
So in regards to the previous question, my suggestion would be to train your device classification model, like whatever you use for that, to also denoise the input signals. So you have your input signal, which was translated wirelessly in a noise manner, and some also gold label, like undistorted input signal, which you make sure is not distorted. And then while you're training your device, your deep learning model to classify which device is sending you the signal, you also train it to reconstruct the original unnoised gold label input signal from the noised input signal. And that sort of is supposed to give the deep learning model an idea of the noise generating process it's dealing with. And hopefully it can sort of cross-reference between the classification and the denoising objective and do better on the classification objective. It's also has the advantage that the denoising objective is much more high dimensional, while that the loss signal is much more fine-grained and complex. It's like training on reconstructing an image as opposed to just classifying an image. So there's that. And then I actually had a question about the content of the upcoming deep learning security course in the winter. If you could just like elaborate on what you intend to cover in that course. Thank you very much.
Yes, thanks for asking that. So since it's a course, it's not actually the full-fledged research. I'm imagining we touch like 3 representative threats that studied in the machine learning security side. For example, adversarial examples and defenses, and data poisoning attacks and defenses, and the privacy attack, which is the membership inference, and defenses. So basically, that help us to understand better like where this the attack comes. So I've seen most of the literature just saying that, okay, neural networks are really sensitive and we should defeat the adversary examples. But there are more than that. Like, for example, adversary example can be studied in the domain, like how we can make the, the model more resilient against the input space, the transformation. And then, like, there are lots of transformations we considered, and can we make some, ensure some invariance on that? That's the other direction. Or the other direction would be like, okay, like, I don't, want to bound the perturbation human imperceptible. So I want to actually go further, like, let's try to perturb anyway, and then try to attack the model. So which is the practical case. There are the things, and there are the interaction between those works, and there are lots of interesting things going on there. So I want to just, to cover all this, the history, and then once you understand that, we try to implement like some of the simple attacks and defenses, or like even try to, to compete each other, like can we break each other's models or not? So these are the things that I want to cover. And also, like, you may participate like group projects, like try to, find how we can work on a certain problem, how we pursue it, and how we communicate the findings in a good way, so that you can become like really good the prospective researcher in this field, so you can start communicating with the people in conferences or whatever. So yeah, that's the the outline that I'm imagining, but like I'm still writing down and making some the course objectives and like content, so it can be the change at any time. Yeah.